All right, let's dive into a really cool concept from vector calculus that, I promise, is way more intuitive than its name makes it sound. We're talking about divergence. It's this powerful idea that shows up everywhere, from how water flows to how electricity works. And by the end of this, you're going to see the world a little differently. Let's get right into it.
So what is divergence really all about? Well, it boils down to one super simple question. If you could zoom in on any single point in space, any point in a river or in an electric field, is stuff flowing out of that point? Is stuff flowing into that point? Or is it all just kind of passing through? That's it. That's the whole idea in a nutshell. To make this crystal clear, think about two things you see all the time. A source is basically a sprinkler head, right? Water is just shooting outwards from a central spot. We call that positive divergence. And a sink? Well, that's just like the drain in your bathtub. Water is swirling and converging inward, disappearing down a hole. That's negative divergence. See? Source and sink.
Okay, before we even think about touching an equation, the best way to really get a feel for divergence is to just look at it. So let's see what these different kinds of flows actually look like when we draw them out as vector fields. Here we go. This is a textbook example of positive divergence. Check out how all these arrows, which show the direction and strength of the flow, are pointing away from that center point. They're literally spreading out. This is exactly what a source looks like, a point where the field is being born. And you guessed it, here's the complete opposite. All the arrows are pointing inward. They're all converging right on that central point. This is negative divergence. It's a sink. You can think of it as a point where the field is ending or being gobbled up. The big takeaway is that there's a net flow into this point. So what happens when divergence is zero? Now, this is important. It doesn't mean that nothing is moving, not at all. As you can see here, you could have a flow that's swirling around like a whirlpool, or just flowing steadily like a river. The key is that for any little area you pick, the amount of stuff flowing in is perfectly balanced by the amount flowing out. There's no net source, no net sink. It's all just passing through. So we've got the visual intuition down. We know what a source and a sink look like. But how do we actually calculate this? How do we put a hard number on it? For that, we need to translate these pictures into the language of math. Let's look at how we quantify this spreading out idea. Okay, here's the official definition. I know it sounds a little dense, but it's really just a fancy way of saying what we already know. Divergence is just a number. It's a number that tells you the intensity of the outward flow, what physicists call flux, at one tiny, tiny little point. It's not just asking, is this a source? It's asking, how much of a source is it? And this is the tool we use to calculate it. Now, this formula might look a little intense, but the idea behind it is actually incredibly simple. All we're doing is looking at each direction separately, the x, the y, and the z, and we're measuring how much the field is spreading out in that one direction. Then you just add them all up. If the final number you get is positive, you've got a source. If it's negative, you've got a sink. Simple as that. Okay, so this is a neat math concept. But so what? Why does it actually matter in the real world? Well, it turns out this whole idea of sources and sinks isn't just for imaginary water flows. It actually describes some of the most fundamental forces in our universe. I mean, divergence is absolutely essential in all these fields. It's how scientists model the way fluids compress and expand. It's how they find the exact location of electric charges. It's how they describe heat flowing from a hot object, and even how they understand the pull of gravity. It is a truly universal concept. And this slide right here is where it all clicks. It's so elegant. In fluids, we said positive divergence means the fluid is expanding. Well, in electromagnetism, positive divergence means you just found a positive electric charge, the literal source of an electric field. And a compressing fluid? That's just like a negative charge, the sink where the electric field lines end. The physics is different, but the math and the idea are exactly the same. All right, let's zoom out for a second. We've been focused on what's happening at single tiny points. But what if we could connect the behavior of all the little points inside a region to what's happening on the boundary of that region? Well, there's a beautiful, famous theorem that does exactly that. This right here is the divergence theorem, and it is a massive, massive idea in both math and physics. All it's saying is this: if you could add up every single little source and sink inside any volume you can imagine, that grand total is going to be perfectly equal to the total net amount of stuff flowing out through the surface of that volume. Let's make that real. Imagine you drop a permeable box into a river. The divergence theorem tells us something amazing.
If you could measure all the tiny little sources and sinks of water inside that box and add them all together, that number would be exactly the same as the net amount of water you measure flowing out through the 6 faces of the box. It beautifully connects what's happening on the inside to what you can measure on the outside. So let's wrap it all up with the big takeaway. It's really this simple. If the divergence at a point is positive, you're looking at a source. If it's negative, you've found a sink. And if it's 0, everything is just flowing through, perfectly in balance. It's the mathematical tool for finding the starting points and ending points of pretty much any field you can imagine. And to finish, I'll leave you with a big thought to chew on. We observe that everywhere we look in the universe, distant galaxies are flying away from us. The whole fabric of space is expanding. That means the divergence of this cosmic motion is positive. So, if you run that idea backwards in time, what does our concept of a source tell you about the very beginning of everything?